My name is Sam Lazarus.
My name is Tyler Ruiz.
Hello, my name is Olaleko Akala.
My name is Aaliyah Davis.
Hello, my name is Nicholas Henry, and we are Team Hermes.
Once again, we are Team Hermes, which stands for Human Extremity Reinforcement and Movement Enhancing Skeleton. Seen here is a picture of our final design. This presentation will walk you through starting at our problem all the way through our solution.
To provide some context, in 2018, there were about 1.14 million US warehouse workers. Around 8,310 have been injured due to overexertion. Overexertion often leads to back pain, muscle strain, neck injuries, sprains or muscle tears, nerve damage, and heart attacks.
Our project sponsor is the Vanderbilt Braun Lab for Advanced Robotic and Control, also known as the ARC Lab. The system that we are working on is the Stronger Legs exoskeleton, which has the purpose of helping humans lift. This is conceptually accomplished by storing energy in a locking spring system as they bend down, storing that energy and waiting until the human decides to lift to release that energy. Our exact project scope is the locking spring system, which is circled on the diagram of the exoskeleton to your right. As Aaliyah mentioned in the previous slide, the primary application for this is warehouse workers, but also has applications to first responders, as well as even space applications on the International Space Station. Now going to exoskeleton operation. As you can see, the white diagram is overlaid on a human diagram of a human lifting a box. So the first step here is the initial condition. Going to step 2, that's the part where the user bends down, storing energy. At that point, that energy is locked in place, and a system outside of our scope changes the endpoints of our spring to maximize the output force. And in step 4, that energy is released. Which now takes us to our problem statement. We are to develop an unpowered spring system with continuous, non-incremental locking to attach to the Vanderbilt ARC Lab Stronger Legs exoskeleton. As you can see, the locking spring system is shown on your right, circled in red. That is our entire scope. We are not concerned with how the ends of the spring change position or kind of the overall operation of the entire exoskeleton. We're solely concerned with our locking spring system. Our locking spring system must be able to lock at every single displacement. We can't have any form of incremental locking. No matter where a human bends down, they need to be able to lock that spring in place in order for the exoskeleton to function properly.
This is a free body diagram of our system in operation. It shows the forces acting on the user as they squat down to pick up a weight. The free body diagram helped infer some of the specifications for our solution. Our design specifications are broken up into different functionalities of our spring system. The first functionality is the max force output. We need the spring system to be able to output at least 100 pounds. This will enable users in the factory setting to lift their average loads found in factories. The spring system needs to be motion compatible. This just deals with how the acceleration and velocity of the spring system compares with the acceleration and velocity of an average user picking up a load. The spring system needs to be empowered. And then under the locking, the spring system needs to be continuous. This is to allow the user lock and unlock at any point along the squatting motion. The locking strength needs to have a minimum safety factor of 2. This is to ensure the safety of our users while they lock and unlock the spring. Given that the spring system is going to be in close proximity with a human operator, we would want to ensure that there are no injuries to the users. And then the spring system needs to have a force output input ratio of 30:1. This just tells us how much force we're getting from the spring compared to how much force required to lock and unlock the spring. This is a measure of the ease of use of the system.
Our final solution to the problem is a hybrid spring system, which will combine the functionality of a coil and gas spring. The coil spring will provide most of the force for the system, and a low force gas spring will be used to lock the system into place. A low force gas spring is used because it requires less force to lock and unlock. The aim is to leverage a lock that is independent from the spring force of the system. Here is our final build of our design. There are 4 main components: the coil and gas springs as described in the previous slide, an end cap that holds the 2 springs together, and then a release system. Shown here is a Bowden wire release system that basically just connects the release button on the top of the gas spring to this push button that the arrow points to, so that the spring can be released with the push button. This is an exploded view of our system showing each component by itself.
We conducted kinematic testing to test the motion compatibility. And in order to conduct this testing, we released the spring from a fully compressed position and measured the position and acceleration. And through this testing, we found that the system can lift just under 50 pounds. And through also doing human trials, we found that the speed of the system was compatible with the motion of a human squat.
Our next test was a force displacement curve test. We needed to test that the compression force of our system actually met our specifications. To achieve this, we put our system into 2 unistrut beams. We then placed that system into the load frame. We compressed our spring system and then recorded the data of the force at each part of its compression. The total compression force was measured at 98 millimeters. We wanted to keep it away from its full compression so that we did not damage our spring. And then after our test, we found that our system did in fact meet our force requirements. The next test was the force to unlock test, and we needed to see what the force required was to unlock the spring system. We placed the spring against a scale and measured the force it took to unlock the system. And what we found that at most it took about 1.5 pounds, which can be easily acquired by any warehouse worker or any other person using the system. The next curve we acquired was the force output versus input curve, and this was measured against the spring displacement. We wanted to meet our design specification for the force output versus input ratio, and that needed to be greater than 30:1. To achieve this curve, we divided the force output by the force to unlock at each of the system displacements. Our results from the experiment and plotting the graph showed that we achieved ratios of 50:80 at all of the meaningful system displacements.
So looking ahead, we found that all of our design specifications are being met. So that means that this design is viable. With this design, we find that there are new capabilities and that a user is able to lift from a squat with amplified force. In application, it can reduce the likelihood of joint damage and work-related injuries.